Natural bodies of water have dissolved carbon dioxide from the atmosphere, which makes them slightly acidic. Rain is also slightly acidic due to the dissolved carbon dioxide from the atmosphere and has a pH of about 5.6. The acidity of natural water bodies and rain can be explained by the equations given. When carbon dioxide gas dissolves in water, carbonic acid is produced, which partially ionizes to produce hydrogen ions and hydrogen carbonate ions. It's the presence of hydrogen ions that makes these water bodies slightly acidic. However, acid rain is a special term used to describe rain that has a lower pH, usually less than pH 5. This is due to gases such as sulfur dioxide, sulfur trioxide, and oxides of nitrogen dissolving in the water. Sulfur dioxide, SO2, and sulfur trioxide, SO3, are two pollutants often found in the atmosphere from the combustion of sulfur-contaminated fossil fuels or from natural sources, such as volcanoes. Sulfur dioxide is usually oxidized to sulfur trioxide in the atmosphere by reacting with oxygen. It's interesting to note that sulfur dioxide is used widely to preserve fruits, such as apricots. Sulfur dioxide reacts with rainwater to produce weak sulfurous acid, while sulfur trioxide reacts with rainwater to produce strong sulfuric acid. We can show the first step in the ionization of these acids to show the production of hydrogen ions that actually makes them acidic. We can also write the one equation using sulfur di and trioxide to show the formation of a mixture of the acids. Oxides of nitrogen, such as nitric oxide, NO, and nitrogen dioxide, NO2, result from high-temperature combustion processes or from natural sources such as lightning. In both processes, nitrogen from the atmosphere reacts with oxygen to form nitric oxide, which oxidizes to nitrogen dioxide in the presence of oxygen. The presence of nitrogen dioxide in the atmosphere often gives a brownish haze. The reaction of nitrogen dioxide with water can also form a mixture of acids, nitrous acid, HNO2, and nitric acid, HNO3. The nitrous acid further oxidizes to form nitric acid, HNO3. The nitric acid is a strong acid which ionizes to produce hydrogen ions and nitrate ions. Acid rain has been observed since the start of the Industrial Revolution in the late 19th century. Acid rain has serious consequences, not just for water bodies, flora and fauna, but also for buildings and structures made of metal or marble. Severe effects of acid rain have been observed in forests in Europe. In the early 1980s, it was reported that about 34% of West Germany's total forest was damaged by air pollution. This included a large section of the famous Black Forest. When trees die, the surrounding ecosystem is affected. Structures of cultural importance are also being destroyed by acid rain. For example, the Greek Parthenon marbles or the Taj Mahal. The equation for acid rain dissolving the marble structures can be written as hydrogen ions from the acid rain reacting with calcium carbonate in the marble to form calcium ions, carbon dioxide and water. Therefore, we can see how the solid marble structure wears away in the presence of acids. Acid rain also contributes to the corrosion of structures containing metals, such as bronze, and the deterioration of paint and stone. For example, structures containing iron can react with acids as shown. The pollution due to acid rain can be controlled. Factories that produce sulfur dioxide from burning coal can use powdered limestone to convert the sulfur dioxide to calcium sulfite, which is then removed as sludge. Alternately, the waste sulfur dioxide can be used to produce the industrially important sulfuric acid. Evidence is based on observations and measurements. Observations on the rapid deterioration since the Industrial Revolution of historical structures as well as flora, such as the Black Forest, confirm the increasing level of oxides of sulfur and nitrogen which contribute to acid rain. Improvements in technology since the 1970s have enabled us to quantify and identify trace amounts of gases as low as 10 to minus 12 parts per part air. The composition of the atmosphere is changing globally, and comparisons made from gas samples trapped in bubbles in ice cores confirm an increase in oxides of sulfur and nitrogen. In the late 19th century, Carl Benz invented what is regarded as the first Benz patent motor wagon or motor car. This invention was significant in that it marked the birth of the automobile industry. It's interesting to note that it was Carl's wife Bertha who, without Carl's knowledge, undertook the first long-distance 180-kilometre return journey with their 2 teenage sons to publicly demonstrate the practicality of the car. The 20th century saw a rapid increase in the use of motor cars, with emissions of oxides of sulfur increasing due to sulfur-contaminated fuel, as well as oxides of nitrogen from the internal combustion engines. There were a significant number of deaths in London in the 1950s due to the heavy acidic smog. Again, this was evidence of increasing levels of oxides of sulfur and nitrogen. In the 1960s, there were also high levels of photochemical smog in big cities with lots of cars. Photochemical smog results when sunlight acts on a mixture of compounds, including oxides of nitrogen. This again demonstrated evidence for the increasing levels of the oxides of nitrogen. Governments soon realised that unless the emission of oxides of sulfur and nitrogen are controlled, serious health issues would result. Hence, modern-day cars are fitted with catalytic converters that reduce emissions, and the quality of fuels has also improved in recent years. For example, it would take about 50 new cars to produce the same quantity of air quality pollutant emissions per kilometre as a vehicle made in 1970. In the US, monitoring air quality from 1980 to 2013 has shown an 81% decrease in sulfur dioxide emissions. Satellites are providing important new information about global nitrogen oxide, NOx, emissions. For example, instruments on the European Space Agency's ERS-2 satellite are providing valuable information, including the levels of oxides of nitrogen. Atmospheric chemistry focuses on studying concentration of oxides of sulfur and nitrogen in the atmosphere. Current data shows the largest source of sulfur dioxide to be from electric utilities, while oxides of nitrogen to be from vehicles. The effects of acid rain remind us to be careful in our choice of car and fuel to help us preserve not only our environment, but also our cultural history.